Dave Pattison. You all know Dave Pattison because he introduced all the speakers before. So Dave is a professor at the University of Calgary in Canada, and he obtained his bachelor degree at the Queen's University, Kingston, Ontario. Then he moved to Europe for a PhD at the University of Edinburgh in Scotland, followed by a postdoc at the University of Chicago. So Dave has a very large spectrum of research interest, but few of the current research interests of Dave are the comparison of observed versus predicted phase equilibria of metamorphic rocks, the interplay between equilibrium and kinetics in metamorphic processes, and he has published some very important contributions, papers on that topic. And also Dave wants to better understand the rocks and even to go one step further to apply metamorphic petrology to deepen our understanding of the thermotectonic evolution of orogenic belts, especially the Canadian Cordillera. So Dave's work is an inspiration for many young scientists, young petrologists, and be sure that I'm definitively one of them. And therefore, I'm very excited about this talk, and I invite you, Dave, to start this presentation. The stage is yours.
Thank you very much for the introduction, Pierre. I'll just share my screen. All right, I hope you can all see this introductory slide. So I'm going to be giving a presentation that's a little bit different than what's been on offered at this point, and it's concerned with equilibrium and kinetics in metamorphism. So I think we have to ask an important question right off the bat. Why are we discussing kinetics when this is a workshop on phase equilibrium modeling? So my take on this is that our ultimate goal is to understand the pressure temperature evolution of metamorphic rocks. And nobody disputes that phase equilibrium modeling underpins this endeavor primarily. But kinetics is increasingly a factor that I think is being recognized, that's something we have to take account of a little bit more than we have. So equilibrium. What is the basic reasoning for thinking that equilibrium prevails in metamorphism? Well, there are a number of lines of argument, but one in particular is the success of the metamorphic phases principle. And that's the repeated occurrence of mineral assemblages in rocks of different composition that have been metamorphosed together. So if you look at this table from Frank Spear's Big Blue Book, for example, if you have a rock in the staurolite zone with a metaphylitic mineral assemblage, you can be pretty sure what's going to be in a metabasite if it's interbedded with that metapelite. And the other thing you notice is that these prograde sequences, like Barovian sequences the world over and at different ages, they usually show the same sort of sequence. And I think it's pretty well impossible to account for this regularity if there weren't, if the equilibrium model didn't at least pertain. But I would say it's in this kind of rationale, it pertains to the peak metamorphic conditions. Now, increasingly, people are interested in the pressure temperature evolution of rocks because they give us more information about how they might have evolved that way tectonically. So the equilibrium model has expanded to embrace the idea that equilibrium is maintained throughout all the stages of a rock's pressure temperature history. This is sometimes known as the concept of progressive metamorphism. So here's a phase diagram that you'll be seeing a lot of in this talk. It's a phase diagram for an average peelite. It's calculated using the Holland and Powell 98 data set with some 2005 AX models. And it's kind of a generic diagram. So thinking of this idea of progressive metamorphism, if you go along this yellow PT path, what you're assuming is that at every point along this path, the mineral assemblage at higher grade develops from the one just below it. This implies that the only reactions that rocks see are equilibrium reactions, the ones on this diagram. And it implies that the rate of reaction and compositional equilibration amongst the minerals, it's always faster than the rate at which the PT conditions change. So this is a more contentious aspect or incarnation of the equilibrium model. And in fact, we all know that it can't be true. And we're thankful for this point. So what are some examples of features that don't follow the equilibrium principle? Well, here are a couple of examples. These are stranded reaction textures. So the top two images are of a coronitic metagabbro, where the olivine and the plagioclase, the original gabbro, they've been subjected to different PT conditions and have begun to react to make this beautiful corona texture. The two images down below, these are from cordierite anthophyllite rocks, and the staurolite, which you can see in the upper left in the two images, it's being partly digested by cordierite. So that gives you some information about perhaps a decompression history for this rock. The other examples we've heard a lot of in this workshop are zoned minerals. So we all know about zoned garnets. If we have zoned garnet, the middle of the garnet is not communicating with the rest of the rock and the matrix. But even more impressive examples of zoned minerals are showing up. And I love these images from Pierre Linari showing zoning in plagioclase, which I think is something that hasn't been appreciated as much as it might have. These are some images from Yang and Rivers 2001 showing different length scales of equilibration for different elements. These are garnet maps, the two images on the left. So this is a manganese map, and it shows a manganese core and a kind of a bell-shaped decrease to the rims. This is a very different zoning profile than the chromium shown in the next image, which suggests a much more localized length scale of equilibration. So this gives rise to the notion of partial chemical equilibrium. And then the last example I'll give is the observational evidence for what seems to be prograde unreactivity, or at least sluggish reactivity of porphyroblasts, even when they are predicted by equilibrium to be reactants to form higher grade mineral assemblages. So if you look at the two images on the left, these are garnet staurolite schists. Garnet is predicted to be a reactant in the formation of the staurolite. But if you look at the garnet in these two rocks, there's very little evidence for dissolution of the garnet. It looks like the staurolite must have grown basically without the participation of the garnet, or at least very much participation. And then the two images on the right, these involve staurolite and andalusite, and one predicts that staurolite is a reactant to make andalusite. But the textural evidence here suggests that the staurolite really isn't dissolving very much to make that andalusite. Now, many of these exceptions can be handled using the concept of local equilibrium, or what Pierre described yesterday as the concept of the reactive bulk composition, or perhaps with the application of chemical potential gradients. So some of these exceptions can be handled, but there are others which can't as easily, and these are really the ones that I'm focusing more on this presentation. Okay, so here's our phase diagram again. What does an equilibrium phase diagram like this not tell us? The first thing it doesn't tell us is the magnitude of the free energy differences amongst the competing configurations. So this is a map of the minimum free energy configuration of this chemical system and bulk composition. It doesn't say, for example, how much this mineral assemblage is more stable than other possible configurations, and especially so as you get close to these phase boundaries. It's just a map of the minimum. The other thing, of course, phase diagrams don't tell us anything about is how long anything took to happen, and how, by what mechanisms, one rock changes into another one as you recrystallize it. So that second question is the domain of kinetics. From our petrological perspective, it's the rates and mechanisms of changing one mineral assemblage into another, how the rock recrystallizes. So just to give a visual representation of what we're talking about. So on the left, we have a chlorite phyllite, and on the right is a garnet schist. And if you heat up a chlorite phyllite enough, you should turn it into a garnet schist. So how does that actually happen? Well, through a series of different steps. And some of them, when you think about them, they're quite impressive. In this chlorite schist, the minerals were, or the elements were arranged apparently happily in crystal structures in minerals. If you're going to change those into a different configuration of minerals, like in the schist, you actually have to destroy the crystal structure of the pre-existing minerals, dissolve them, transport the ingredients in appropriate proportions through some sort of a medium to the site of potential nucleation so that you can grow the new mineral phase. And it's really quite a series of steps. It's quite a feat, really. So in terms of this process, there are a couple of kind of two main classes of energetic factors involved. So the first one is there has to be free energy driving force. So if we're going to turn the phyllite into the schist, the schist has to have a lower free energy than that of the phyllite. So there's a free energy difference between the two, shown here by the delta G term. So that's the driving force for the reaction. Well, then there's this other energetic barrier that has to be overcome. You have to break apart your pre-existing minerals and transport the products and nucleate them. And that is a barrier, an energetic barrier known as the activation energy barrier. And for any reaction, a rate of a reaction is a balance between these two different energetic terms. There's the free energy driving force term, and this is the activation energy term. This is the general kinetic rate equation, and it's based on transition state theory. So there's our free energy driving force term, and that is the activation energy term. And there is a different activation energy for each step in the kinetic process. So let's just have a short look at those different components. Okay, so broadly speaking, you can divide these different steps of a kinetic reaction process into a couple of main groups. There's one which involve what are known as approximately linear rate laws as a function of the temperature overstep. This is if it's not too large an overstep. And basically, the rate of reaction is proportional to the size of the temperature overstep. So it's really this first term that we're focusing on here. The second term we're assuming doesn't change that much over the range of the temperature overstep. It does change with absolute temperature, that's the Arrhenius relation, but maybe it doesn't change that much. And the absolute values will vary amongst these different processes. Then there's nucleation, and it's kind of a different story. In addition to the rate being proportional to the temperature overstep due to this first term here, the activation energy term itself is a function of the temperature overstep squared. So you multiply the proportionality incorporates this, what I call a turbocharged exponential rate term, exponent of delta T squared. And the consequence of this is shown in this diagram that Dave Waters has on his tutorial site. And what it's showing is nucleation rate on the vertical axis against temperature overstep on the horizontal axis. And the consequence of this turbocharged exponential rate law is that there's an interval of no nucleation and then a very abrupt increase. Now, this rate law, or illustrated in this diagram, this is for homogeneous nucleation in a homogeneous medium. So that's an obvious simplification compared to metamorphic rocks, which have got a range of different types of nucleation sites of varying preferability, and perhaps involves heterogeneous nucleation involving more than one phase. So those exceptions aside, the basic difference between these rate laws still pertains. Okay, so here we have equilibrium on the left. This is the equilibrium phase diagram. And then we have kinetics on the right, which is saying basically none of these reactions can proceed because or without some sort of an energetic push because of this activation energy barrier. So here's the fact, perhaps uncomfortable. Every reaction has to be overstepped to proceed. So from our perspective as petrologists, really the only question is, or the main question anyway, is how much? Is it petrologically significant? Does it affect how we interpret the evolution of metamorphic rocks? Like, do we care? So one question is, well, how much overstepping is needed? And another one is every reaction on this phase diagram, is it overstepped by the same amount? So the answer to that is related to the two different energetic components of the rate equation. First of all, it's related to the activation energy barrier of the rate limiting process. And I would draw special attention to nucleation in this case for the reasons I gave. And the second term is this one, which is the free energy driving force for reaction, which is sometimes known as reaction affinity. And this is expected to vary across the phase diagram because of the different range of reactions. So just to go through how this works, the panels on the left are schematic diagrams. The one on the upper left is a schematic phase diagram. And this is showing a schematic garnet-in reaction. So to the left of the red line, we have the reactant assemblage, muscovite chloride biotite quartz. And then to the right, we've got the garnet-bearing assemblage. The horizontal line here in black is an isobaric path of increasing temperature. Okay, let's look at the second panel. This is free energy versus temperature. And there's a couple of different sloping lines here. This first one here, this is for the reactant assemblage, muscovite chloride biotite quartz. And then there's another one here, which crosses over this dot. This is with the free energy versus temperature service for the garnet-bearing assemblage, the product assemblage. Now, if equilibrium pertains, we assume that we're always hugging the bottom of the free energy surface in the system. And so one would, with increasing temperature, migrate to here. The two lines cross over, and that is the equilibrium position of the reaction. And so that's where we would fall on the upper panel, right on the reaction. Now, supposing there has to be some overstepping, as we know there does have to be. So then in this case, one would, I seem to have lost my cursor here. One would track along this muscovite chloride biotite reactant free energy surface, overstep the reaction. And then as the more you overstep, you can see that there's more of a free energy difference between this metastable reactant assemblage and the stable assemblage. And that energy difference represents this thing called reaction affinity, which is this energy that needs to be added to the system to overcome these barriers to reaction. So coming back to our phase diagram illustration, so we overstep the reaction along this line, and then eventually it goes, and that would be represented by this point here. So reaction affinity built up to this point here, and finally we overcame the barriers to, say, nucleation perhaps, and garnet started to grow. The lower panel is the reaction affinity versus temperature diagram, and while we're tracking or starting in the lower temperature, there's no buildup of reaction affinity because we haven't reached a reaction yet. We hit the reaction, and as we overstep it, the reaction affinity builds up to the point where it overcomes this horizontal dashed line, which is the threshold for reaction to occur. At that point, reaction finally takes place, and then it drops back down, perhaps closer to equilibrium. Okay, so I'm focusing on temperature change here. And in this case, if we have temperature change, since free energy varies as a function of temperature according to the entropy change, the reaction affinity that builds up is equal to the temperature overstep times the entropy change of whatever reaction is being overstepped. So how does this vary between different reactions? Okay, that's what's shown in this diagram here. So the vertical axis is reaction affinity. The horizontal axis is the temperature overstep. And there are a whole series of different sloping lines here. The ones with the steepest slope build up the reaction affinity the fastest. And these are the ones that have the highest entropy change. And you can go all the way down to reactions with very low entropy change, and those have the lowest slopes. These broadly correlate with how much water is released in the reactions, which itself kind of is correlated with what the reactant minerals are. In this case, this steepest slope line chlorite is a very hydrous phase, and so the reaction that makes andalusite biotite releases a lot of H2O, which is a highly entropic phase. Now, let's suppose there's some sort of a generic energetic barrier to nucleation and growth represented by this dotted line, say 300 joules per mole oxygen in the porphyroblast. So how much overstepping is needed to achieve that? Well, if we start with this high entropy reaction, which has the steepest slope, the amount of overstepping that has to be achieved to creep up to that level is about 10 degrees, not that much. For the blue reaction here, which has a lower slope, the amount of overstepping required to hit that one is a lot more. So you expect that basically it's going to vary from reaction to reaction. Now, this principle is very similar to what Dave Waters was talking about in terms of the uncertainty on the position of phase equilibrium boundaries based on the difference in the energy of the mineral assemblages on either side of a reaction boundary. So just to give two examples here, this diagram illustrates the difference in the free energy as you cross the garnet in reaction, this one here in the phase diagram. So you only increase the energetic favorability of the garnet mineral assemblage quite modestly as you go above that curve, and that's in comparison to this one here, whoops, which is the chlorite to staurolite reaction, where it increases much more rapidly. So the two kind of this is quite tightly tied to this notion of reaction affinity. The uncertainty on these reactions is kind of bound up to how quickly the energy changes as you overstep them. Okay, so how much variation is there in increase in reaction affinity with overstepping amongst the reactions on this diagram? So I'm just going to focus on this one little portion of this phase diagram, and that's shown here. So here's the chlorite to garnet reaction, chlorite to staurolite, staurolite to aluminosilicate, and so on. This image shows it's the same diagram as before, but I've color coded it. So the most entropic reactions are in red, intermediate in orange, and low in blue. And so if you superimpose those back on the phase diagram, you can see that there's a variety of different sorts of behaviors expected. So I'm going to look at three examples, showing some reaction affinity maps for three examples. So there's the diagram and same phase diagram. Let's first look at this one, which is a reaction in which andalusite is formed from the breakdown of chloride. This is a highly entropic reaction. The colors represent the increase in reaction affinity with overstepping. So you have to imagine that you increase in temperature, you overstep the boundary, and you look at how quickly the affinity builds up with overstepping. So these contours are labeled according to 100 joules per mole in andalusite. Okay, let's look at the blue reaction here. This is also forming andalusite, but the reactant in this case is staurolite, which is a much less hydrous phase than chlorite. And so it's a less entropic reaction, and the rate of buildup of reaction affinity is much slower for that reason. So the contours are more widely spaced. And then a third example, which is quite extreme, is this one down here involving andalusite, biotite, and cordierite. And here, the amount of the rate of affinity buildup with overstepping is very small. And so one could pose the question, would you even ever see this reaction if there are significant kinetic barriers to its progress? Okay, so that's the theory. The real question is there actually petrological evidence for kinetically controlled overstepping? Is it important? What might be some of the consequences for our interpretation of metamorphic rocks? And the last one is, does it occur in regional and contact metamorphism? So let's begin with this paper, which really completely changed my outlook on this whole question. This is a paper by Dave Waters and Dave Lovegrove, and they were looking at polytic mineral assemblages in the contact aureole of the gigantic Bushveld complex. So they were looking at individual samples, and in particular, they were looking at the microstructural record of the growth and consumption of the porphyroblasts. So here's an image from their paper, which I'm not going to explain each of these. I'm just going to explain one just to show some of the reasoning that went into how they could build up this sequence of reactions. So we'll focus this one in the red box. So here's a nice color photomicrograph. So we have here in the middle a staurolite porphyroblast in kind of yellowish. It's surrounded by andalusite, and there's biotite over here in the upper left. Now, if you look in the staurolite, you can see that there's different patterns of inclusion, density, and distribution. So in this portion of the staurolite, this has overgrown a shape which is unmistakably that of a pre-existing chloritoid porphyroblast, which existed in the lower grade rocks. Now, then there's another part of the staurolite which has a more dense collection of inclusions. But in the upper left, you can see some staurolite here with some coarse inclusions. This is, has evidently overgrown this biotite based on the similarity of the inclusion distribution. So you can work out a series of kind of a history of the evolution of this rock by putting together these various lines of argument. If you put the whole thing together, or they put the whole thing together, this is what they came up with from the textural analysis. So here's modal proportion of minerals versus time, or if you like, that could be a temperature axis to increasing temperature. So the lower grade assemblage had chloritoid and chlorite, and the final mineral assemblage had a staurolite, andalusite, biotite, and some cryptic cordierite that comes in, which I will probably not talk about at length, but it's quite an interesting observation in itself. Okay, so what did they do next? Well, they took this bulk composition and they calculated a phase diagram and tried to examine what's the predicted sequence of equilibrium reactions for this bulk composition at a pressure that would match the production of the highest grade mineral assemblage, what looked to be the final stable mineral assemblage. And that was at about 3.25 kilobars. So that's the predicted sequence of growth of the minerals. So from left to right, modal proportion on the vertical axis, increasing temperature to the right. So starting with chloritoid and chlorite, you can see that there's a predicted sequence of mineral growth and consumption reactions that looks completely different from what was interpreted from the textures. So there's the predicted mineral growth consumption sequence. And the next step they did was to calculate the positions of the reactions interpreted to form the biotite, andalusite, and staurolite bearing mineral assemblage. And the result of that is this. So same temperature axis along the bottom, but instead of all these reactions occurring down here, the chloritoid and the chlorite basically persisted upgrade until finally they reacted out in this kind of cascade of reaction here. So there are the equilibrium reactions, and those are the overstep reactions. And the amount of overstepping in some cases is quite substantial, up to 80 degrees C for the comparing the lowest temperature reaction to the highest temperature one. And the next, and I thought most ingenious part of this paper was the way they rationalized it. And so they were interested in this idea of buildup of reaction affinity. So the vertical axis is reaction affinity, the horizontal axis is temperature axis, and the different sloping lines represent the different entropy change of the reaction and the rate at which you build up reaction affinity when you overstep them. So if everything worked according to equilibrium, the first reaction that would have been encountered was this one. Chloritoid goes to andalusite chloride. Well, apparently this was overstepped, so reaction affinity would be building up along this reaction. And at this point, other reactions become thermodynamically possible. And their interpretation was that this one, reaction 5, which has got a very steep slope, it basically rapidly increases reaction affinity to the point where it overtook, in terms of reaction affinity, this lower grade reaction. And this is where the main bulk of reaction took place. Finally, the product faces were nucleated, fluid was released, and there was a vigorous interval of reaction, which included the consumption of the otherwise recalcitrant chloritoid. So that left a big impression on me because I felt it was the first time I'd really seen good evidence of like petrological evidence for the importance of kinetics. So another example I'll show comes from the Nelson contact aureole in British Columbia. And this is quite a large intrusion. It's not as big as Bushveld, but it's about 40 kilometers by about 60 kilometers. And we'll just focus on the contact aureole in this red box. So the next map is a blown up map of that. Okay, so here's the map. There's the Nelson batholith on the right. There's a scale bar. The dots represent samples, and the lines represent isograds based on the mineral assemblages. Like Waters and Lovegrove, we took a bulk composition of these very uniform rocks, I might add. These are graphitic argillaceous rocks, and calculated a phase diagram. This is the phase diagram I actually showed earlier. And posed the question, what sort of a PT path would you need to satisfy at least the occurrence of the mineral assemblages in the contact aureole? And there's a range of pressures, but this red line kind of is in the middle. And it doesn't matter whether you have a slightly higher or lower pressure, the inferences are pretty well the same. So the next step was to take the predicted equilibrium reaction intervals shown by these blue dots. This one, for example, is the incoming of garnet. This one is consumption of garnet, actually. But to then compare what you would predict the isograd sequence and spacing to be compared or based on that. This required some sort of a thermal model away from the heat source. And here are the predicted positions of the reactions with the blue dots corresponding to the phase diagram. So that's really quite different. The distribution of the isograds is quite different than what's observed. Rather than all of these reaction intervals, in reality, there were just two main reaction intervals in the contact aureole. This bunched up collection of garnet, staurolite, andesite in, and this is where staurolite finally gave up and volumetrically reacted out to silimonite. So this is the same phase diagram showing those two intervals of reaction instead of these multiple intervals of reaction. So the first main kind of clumped reaction was this one, where these various porphyroblasts grew from chlorite consumption, a little bit overstepped. And then there's this one in which staurolite finally gave up, even though it was predicted to be consumed at much lower grade. So this diagram kind of summarizes the situation. There were some zones of overstep reaction. So in this red or pink interval here, the predicted equilibrium position is the dashed line. The observed position of garnet in is the solid red line. For the next zone up, the predicted position of the staurolite to aluminosilicate reaction is here, where it actually took place was up here. So in both cases, there were mineral assemblages which were metamorphosed to conditions, to higher grade conditions than indicated by or predicted by the equilibrium assumption. So one could pose the question, does this mean this is a violation of the metamorphic facies principle? The mineral assemblages are not developing, or the rocks are not developing the mineral assemblages that you predict according to equilibrium. And so in a way, I suppose you could say yes, because they're not forming, in other words, the mineral assemblages of the rocks could be not reflecting the higher grade conditions they experienced. But in practice, it might not affect things that much because the sequence of the development of the mineral assemblages is still pretty much the same as what you find in other sequences around the world, but the spacing has been changed. Okay, so let's come back to our the various questions we posed. So is there petrological evidence for kinetically controlled overstepping? In my view, yes. I've shown you two examples, and there are others which I haven't described. How important is it? Well, in some cases, it looks like it could be quite important. If 80 degrees overstepping is significant to you, then that's quite important. And the amount of overstepping also seems to be a function of this, the entropy change of the reactions. So Given this, what are some of the consequences? Well, one is onset of reaction can be delayed by petrologically-significant degrees. So in some cases, this carries implications for how we estimate the PT conditions of metamorphic mineral assemblages. If the staurolite-bearing mineral assemblage in the Nelson contact aureole didn't develop the aluminosilicate mineral it should have, one could interpret that it formed at lower temperature than it actually experienced. A second implication is reactions other than those in equilibrium phase diagrams are possible. This was shown in the Bushveld complex. And this has a big implication for our increasing use of textures and mineral inclusions in metamorphic rocks to deduce PT paths. If we just think of the equilibrium reactions, maybe we're missing something. A third implication is that rather than there being continuous equilibration and compositional equilibration and so on, instead, it may be that there are discrete intervals of reaction and fluid release that are episodic. And in some cases, they may not bear obvious relationship to the equilibrium phase boundaries. And an example of that was the Nelson contact aureole. So the implication here is that for those interested in the behavior of fluids in the Earth's crust and fluid movement and release and so on, this has implications for when this fluid release actually happens. And there's another implication here that is kind of related to the last one, and that is that perhaps most of the reaction, or much anyway, the reaction that we see in metamorphic rocks through their history, maybe this just occurs at a few discrete intervals marked by these high entropy change dehydration reactions. And these are the sorts of reactions which actually define or bound the metamorphic facies. And yet within the facies themselves, maybe there's less reaction or more overstepped reaction. So this is illustrated in, this is Frank Spear's facies diagram again. So I've highlighted in red here the green schist to amphibolite facies transition. This is typically marked by chloride consuming reactions, which are highly entropic. And based on a rather small survey, since there aren't that many studies out there, if you look at the degree of overstepping that occurs within the facies on either side of that transition compared to on the reaction or on the facies boundary itself, it seems like there is more overstepping in the facies themselves than in this facies bounding chloride consuming interval. This kind of leads into the next question, which I've often had posed to me is, does overstepping occur in regional metamorphism as well as in these contact metamorphic examples you've provided? I think the first step to address this question is what are some of the differences between contact and regional metamorphism that might influence the way in which rocks recrystallize? So one factor that everybody talks about, and it's probably true, is that generally speaking, heating rates are likely to be slower in regional metamorphic terrains than in contact metamorphic terrains. Now, granted that, there still is the point that, for example, say for nucleation, heating rate is not the critical factor in determining the amount of temperature overstepping. It's this turbocharged rate term related to the temperature overstepped squared. So to underscore this point, this beautiful example of the Bushveld aureole, which show these beautiful textures and overstepping relationships, that is a gigantic intrusion, and the time scale of metamorphism there actually approaches regional time scales. So rate of, the rate of heating, this probably influences the texture of the rock, but whether it actually influences when the reactions actually take place is a more difficult question. The other factor in regional metamorphism that may be important is the fact that, generally speaking, there's an enhanced deformation during the regional metamorphic thickening and heating process. And this can create things like defects, increased strain energy in crystals, maybe damaged crystal surfaces, And these are interpreted by a number of people as having the potential to lower kinetic barriers to nucleation and growth, perhaps leading to smaller degrees of overstepping. So here are just a few photomicrographs showing this. Here's a nice granulated low-grade, looks like phyllite or semi-peelite. Here's a nice garnet, which is overgrown a beautiful granulated fabric. And this diagram, or a photomicrograph on the left, shows a foliated rock with porphyroblasts. Well, these are cordierite porphyroblasts. So this is actually a deformed rock from a contact aureole. So it's not really valid to say that all regional metamorphic rocks can be deformed and contact metamorphic rocks are never. Well, here's an example showing a deformed contact metamorphic rock. That said, maybe these general points do pertain. Okay, so I'd just like to show one example of regional metamorphic mineral assemblages, which I think have been or could have been affected by kinetic processes. And this is quite an important one. This relates to staurolite and aluminosilicate minerals. And these are determinants for many Barrovian versus Buchan type terrains. So here's our same equilibrium phase diagram for an average peelite. And if you calculate these sorts of phase diagrams using different thermodynamic databases for a range of different bulk compositions, you end up with a very similar interpretation based on or concerning staurolite aluminosilicate relations. And that is that the first appearance of an aluminosilicate mineral, up here kyanite, or here sillimanite or andalusite, comes at the expense or with staurolite as a reactant to make the kyanite or the sillimanite by this red reaction. Muscovite staurolite quartz goes to aluminosilicate garnet biotite. So basically everything below this red line, aluminosilicate minerals are not stable. So that's the prediction. Now there are at least two problems with this. I think there's more than two, but I'll focus on two. Here's the same phase diagram. So what do you anticipate in terms of metamorphic sequences, in terms of development of these mineral assemblages and how widely developed they are? Well, first of all, up here, this is a schematic metamorphic field gradient for Barrovian sequences that develop kyanite upgrade of staurolite. This is a high pressure Buchan sequence, high pressure because it's got staurolite rather than cordierite. There are lots of examples of these. So lots of examples of Barrovian sequences, lots of examples of Buchan sequences. Well, one anticipates that there should be a whole collection of metamorphic field gradients that go through this big gap between those two, where staurolite gives way to sillimanite along this red reaction, but it doesn't contain any kyanite or andalusite anywhere else in the prograde sequence. Okay, you go through the middle. And here's the reality. If you look at the range of documented prograde mineral assemblage sequences, there are very few of these. The second problem is just looking at the thin section. If you look at thin sections of staurolite, kyanite bearing rocks, I encourage all of you who have these mineral assemblages to do this. In many cases, I'm not saying in all cases, but I would say in most cases, there is very little evidence that staurolite is the reactant to make the kyanite. In this upper left image, the kyanite looks like it basically grew contemporaneously, or at least independently, from the staurolite. Same in the upper right diagram. This is a fairly clean staurolite porphyrblast. Admittedly, it's got a bit of a hole in it. Kyanite over here. There's no indication here or anywhere else in the thin section that the staurolite was the reactant for the kyanite. These lower images I showed earlier, these are the staurolite andalusite rocks. And again, I would say there's no evidence that the staurolite is the reactant phase to grow this andalusite. So this is quite a common observation in my view. I'd be happy to show otherwise, but this is what I and I think a number of other people have found. So the implication is the kyanite had to grow from something else. And what are you left with? There's not that many choices. And the best possibility is matrix minerals, meaning possibly muscovite and chlorite and the like. So here's the same phase diagram again. There in red is the equilibrium predicted reaction that introduces, say, kyanite. This reaction 9 here, this is the predicted stable muscovite chlorite consuming reaction to make staurolite biotite. Now, this dashed line here in blue, this is another muscovite chloride consuming reaction, but it produces an aluminosilicate mineral. For example, up here, kyanite. There's not a big difference there's not a big temperature difference between these two. Maybe 10 degrees. So if you have a muscovite chloride mineral assemblage and you overstep this first one by 10 degrees, then you enter into a PT regime where you can lower the free energy of the system by reacting those same muscovite chlorite minerals to make kyanite instead of staurolite. Now, there's another reason that might favor this, and that is if you look at the crystal structure of staurolite, its crystal structure consists of alternating bands of kyanite in kyanite structure with aluminum hydroxyl iron bearing layers. So you could pose the question, maybe it's easier just to make the kyanite rather than making the more complicated structure that contains kyanite structure within its own crystal structure. There's other evidence from just the distribution of isograds, not everywhere, I should point out, but in a number of localities, quite a few, the two minerals appear to come in as you go upgrade at the same time, or you can't distinguish the incoming of the two minerals. Now, I know this is not without exception. There are many examples of staurolite bearing mineral assemblages or zones that occur below a kyanite zone, but there are also many examples where the two seem to come in together. So a consequence of this is that rather than kyanite staurolite bearing mineral assemblages being forced into this fairly high PT region, corner of the phase diagram, and Buchan assemblages in this dark gray area down here, if we produce these aluminosilicate minerals by these kinetically controlled reactions consuming muscovite chlorite to make kyanite, say, then the extent of Barrovian metamorphism can go down in temperature and pressure by quite a lot. And the effect is you narrow the gap between Buchan and Barrovian to this red interval of a kilobar. These are just predictions, so I'm not saying that's super robust, but at least it's narrowed compared to the equilibrium assumption. And to me, that's worth thinking about, given this observation that there's so few sequences that go through here. Maybe it's because it's a narrow gap. So coming back to our questions, I'm not going to repeat all the first three. I think I hope you're convinced that there's some evidence of kinetic control on metamorphism. But this last one here, does kinetically controlled overstepping occur or influence what's gone on in regional metamorphism? I would say potentially yes, but I don't think it's being considered perhaps as much as it needs to be. I'm going to finish with one question which I think motivates many people in this audience and those who are not in the audience, and that is how much overstepping is needed to produce garnet? How much is the initial garnet forming reaction overstepped? So a number of groups have worked on this, and I've worked a little bit, but not nearly as much as others. But I'd just like to try to give an overview of what's been found. So this is a table going from the left, from older studies to more recent studies on the right. The yellow represent the different sort of settings where this question is being posed. So regional Buchan terrains, Barrovian, contact aureole, a variety of regional settings, blue schist facies, Barrovian, and then in Frank Spear and Adrian Castro and Oliver Wolf's group, Barrovian and blue schist metamorphism. Now, a number of different approaches have been adopted to address this question. This early study was based on phase equilibrium modeling comparison of the interpreted formation of garnet compared to where it was predicted to first develop. The study by Wilbur and Ague was concerned with, they were simulating the growth of these interesting branched texturally sector zoned garnets. I've mentioned to you about the Nelson contact aureole, the relative displacement of the isograds in an equilibrium and an overstep situation. This is a substantial study by Kelly et al. Looking at crystal size distributions and numerical modeling based on that of possible overstepping of garnet nucleation and growth. This is an interesting study by Mark Kinetic, presented in Carlson et al. 2215, in which he used garnet isopleth intersections of the largest garnets in the rocks and compared that position shown by these intersecting isopleths with the predicted garnet N curve here shown in the dashed line. There was a study by Freya, George, and Gades, an absolutely sensational study of crystal size distributions, chemical zoning, and numerical modeling. Their conclusion was the amount of overstepping was very small. And then there's a series of papers using really quite a kind of a different sort of approach, focusing on inclusion-based barometry, QUIG, and trace element-based thermometry combined with phase equilibrium modeling to try to address the same question. So out of all of these studies, the range of estimates, as you can see, is quite variable. 80 degrees C for this earlier study. Wilbur and Ague didn't specify an amount of overstepping. We suggested maybe 30 degrees in Nelson. Kelly and al. Found a range of estimates. Mark Kinetic's study suggested maybe 80 degrees overstepping in several kilobars. Negligible, as I say, for George and Gades, and 20 to 80 degrees C and 2 to 8 kilobars from these studies. This embraces both Barovian and blue schist studies, and the larger degrees of overstepping, interpreted overstepping, were for the blue schist setting. Interestingly, quite similar to what was inferred by Mark Kinetic in the blue schist. And actually, I think they both looked at Sifnos blue schists, if I'm not mistaken. Okay, so what's the upshot of all this? I'm not really sure what the upshot is, other than there's a range of different estimates. But I would say that, what is common to all of these approaches? Well, if you're going to be interpreting overstepping, you have to overstep something. And the something you're overstepping is the equilibrium position of the garnet inline. And I think this might be part of the answer to the question as to why there are such diverse estimates. And that's because this is very hard to pin down. And I'll just put up this series of diagrams that Dave Waters showed in his presentation yesterday. This shows different predicted garnet stabilities for exactly the same rock composition, exactly the same chemical system, but just varying the thermodynamic database. And in fact, in some cases, not even varying that, just varying the activity composition models for garnet stability. And without going into the details, you can just see that it really varies a lot. So I don't really have much of an answer for this, other to note that it's a difficult question, and I think we just have to keep on thinking about it. Okay, so I think I'll wrap up here. So what are the conclusions of all this? Well, the first one is, even though you can kind of tell that I think kinetics is an interesting factor to consider in metamorphism, this doesn't change the fact that phase equilibrium modeling remains the foundation for what we do in terms of analyzing the pressure temperature evolution of metamorphic rocks. But I would say that metamorphic crystallization is an interplay between equilibrium and kinetics. And so I think it's just worth accepting that kinetics may have a role to play in the compositions and textures and evolution of metamorphic rocks. And it hopefully should provide better interpretations. And I think equally, it might avoid some misinterpretations. So on that note, I think I will stop. And here is the series of cited references in the presentation. And then I've added a few other references after that. So if you're interested, you can find these on the the PDF that's posted on the workshop website.
Okay, thank you very much, Dave, for this comprehensive overview of the problems, of several problems related to these kinetic effects. And we have several questions to you, and it will be an intense discussion. But I want to start with a very general question, and I'm also interested is, how do you calculate those lovely reaction affinity maps that you showed in your presentation?
Okay.
If I want to do that, how can I do it?
Right. Okay. Well, I'm kind of glad that I kind of thought this question might come up, because I have some slides a little bit later on. Right. So this this diagram here shows three different approaches that we adopted. So this is a PT phase diagram. Here's the garnet in reaction. And so if you go up temperature along this blue line and you overstep the reaction, you know, how can you calculate the rate of increase of reaction affinity with overstepping? Now, oh yeah, so this diagram in the upper right, this is the another phase diagram, but it has been calculated in which garnet was suppressed. So think of this as the garnet-free phase diagram, and this is the garnet-bearing phase diagram. So when you overstep the garnet inline, you're to the left of that curve, you've got the reactant assemblage, which is chlorite, biotite, muscovite. Okay, and this phase diagram here, there's the same blue line. So if you overstep the reaction, then you still got the reactant assemblage to the right of the predicted red line. Okay, so one approach is you subtract the free energy of the garnet-bearing assemblage, whoops, up here, from the free energy of the garnet-suppressed assemblage. I think this is the most common approach that's adopted. I think that might have been what Mark Kinetic adopted in his example, and some others have been adopting. So you just subtract the two free energy surfaces, kind of like that G versus T diagram I showed early on when I was outlining the reaction affinity. Okay, so that's one. That's probably the easiest approach. The second approach is you fix the composition of the reactant assemblage, muscovite, chlorite, biotite, right at this curve, and you fix that, and then you subtract the free energy of the garnet-bearing assemblage from that. That was approach 2. And then there's approach 3, and that is where you exclude garnet from the equilibrium assemblage. So you're concerned with the garnet absent muscovite, chlorite, biotite assemblage, and you just monitor it relative to the free energy of the garnet free assemblage. So I've got a picture here, I hope. Yeah. So what we're doing with this third approach, it's sometimes called the parallel tangent method, but this is a schematic diagram. So this is free energy versus composition. These are two schematic G versus composition surfaces for the matrix and for garnet. So if you're below the garnet in line, then the free energy of the matrix has got a lower free energy. But supposing we've got this composition of the matrix. As you increase the temperature, garnet starts to move down relative to the matrix. And so here you've got both coexisting. This would be the equilibrium garnet in boundary. In this case, where you've gone above the garnet in line, then the garnet free energy surface is below that for the matrix. And the more you overstep, the more that goes below the this tangent for on the matrix GX surface is the for that particular matrix bulk composition. So in this model, this is called the maximum driving force method. And so you assume that the garnet that actually forms is formed at the composition that provides the maximum energetic driving force. So that's this third approach. We did a comparison between these three different approaches. And you can calculate a simple sort of n-member K-mash or K-fash entropy change for the reaction. In fact, Dave Waters did this originally in his 2002 paper. And then we compared the results from these three different methods. And the one that seemed to reproduce what you get from the simple calculation was this method 3. And this is the one that we adopted. And this probably pertains most accurately to the energy that builds up when you don't nucleate. There's other arguments for favoring this, the simpler method, but that's basically how he did it. And so those reaction affinity diagrams come from that third approach.
Okay, thank you. So if I understand correctly, in the third approach, you still calculate the difference in Gibbs energy between two equilibrium states, one without garnet and one with garnet.
Well, they're not really two full equilibrium states. In this situation here, if you're right on the garnet inline, if that's the GX surface for garnet, and there's the GX surface for the matrix. This is a simplification because a matrix is a multi-mineral substance. On that line, then the composition of the garnet, it will form a different composition than the matrix, but it is predicted to occur at the point of mutually tangential chemical potentials in the two domains. So in this situation where we look at the garnet has come below, we've overstepped the curve, there's the dashed red line. That would be the equilibrium position. The position for the maximum energy driving force, the biggest free energy kick, is you assume that the garnet forms out of this matrix with its with the chemical potentials according to this tangent, and grow the garnet of a composition which is a little bit different than the predicted equilibrium composition, but it's the one that gives the maximum driving force. And that's shown even more kind of extremely here, where the dashed red line is the equilibrium position, and this is the maximum energy driving force composition.
Okay, thank you very much for the clarification. The next question is, how do reaction affinities for decarbonation reaction vary from the dehydration reaction that you have focused on in this talk? Do you have any comment?
That's a great question, which I've not really thought about in detail. I mean, thinking of reactions in carbonates, the immediate thing that comes to my mind is that many of these are related to change in fluid composition. So just to make that point, but say like dolomite quartz goes to diopside plus CO2, that's a simple reaction, or maybe calcite quartz goes to elastonite CO2. So the question is, what would be would one anticipate overstepping similar to what I'm suggesting might have happened in the P-lights? And I don't really know. I haven't thought about that. Like for me, I'm a petrologist, so I would always want to be looking for, is there some field example where you could trace, say, I don't know, a dolomite quartz layer upgrade and see if there's something funny about the order of the isograds compared to other changes, or maybe something in the textures. But there has to be some overstepping. We know that's a fact. Overstepping happens. It's just how much. And I don't know, maybe carbonates recrystallize a bit more easily. So I don't know about the nucleation kinetics of diopside very much. So I'd have to defer to some others on that question.
Thank you, Dave. The next question is, if dissolution precipitation is the reaction mechanism, shouldn't we consider the possibility of a variable activity of H2O in varying the activation energy needed for overstepping?
Yes, for sure. So I'm sure that'll have an effect. The question I would pose is, what is going to be changing the activity of H2O in that particular case? So if you're dealing with a metapelate that you're heating up, and the the main phases are hydrous phases, then one anticipates that the main fluid phase is going to be H2O. Maybe there's graphite, maybe there's a bit of carbon-bearing fluid species mixed in there, but in terms of controlling where a reaction might occur, I think that's going to be dominated by the internally generated composition of the fluid, which I would think would be water dominated. So if you have fluid infiltration, that's something different.
Thanks, great. So the next question comes more from a modeling perspective. So it seems like at the peak of metamorphism, the mineral composition are thought to be equilibrated, but the modes or sometimes even the assemblage may not correspond with the phase assemblage diagram prediction at that PT condition. So does that point support a greater reliance on mineral compositions rather than mode assemblage or assemblages for estimating PT conditions?
Well, thank you for that question. Maybe you want to answer it. Well, I think, to me, Pierre, I think you addressed this, well, you and Dave Waters both addressed this point really well in your presentations, is that in terms of robustness of phase equilibrium modeling, it seems like mineral compositions are more robust than modal abundances, and both determine how the predicted mineral assemblage. I find this a very, very interesting, important point, because thinking back to the metamorphic phases principle, that's kind of based on mineral assemblage, repeatability, consistency amongst mineral assemblages. And so if you work it backwards, it means there has to be quite a lot of consistency amongst mineral modes and finally into mineral compositions. Maybe it has to do with, or the question was more with modeling PT conditions. So could you have a rock that gives reliable, say, isopleth intersections? A garnet-bearing rock contains reliable isopleth intersections when, say, it didn't grow the aluminosilicate for kinetic reasons that it should have. Like, could you still get a reliable PT condition out of a rock that doesn't have the right mineral assemblage? And I suppose you could. And my impression for saying that is strengthened by what I've heard in this workshop. You might not have the phase you want to have maybe it didn't nucleate, but perhaps you could still get a PT estimate that's reflecting the conditions that the rock experienced, even though one of the phases didn't nucleate. It kind of offends my sense, or this consistency idea that you want the PT estimate to be consistent with the mineral assemblage, but in some cases, I think I might have given some examples, I don't think the mineral assemblage grew that should have grown. Whether this was out by 20 degrees or 10 degrees, maybe nobody cares. If it's 50 degrees, maybe you start to care.
I'm glad you answered this question, because you take it from a slightly different perspective, and that's great, I think, for the participants. Oh, let's move on to the next question. You talked a lot about temperature dependency to the process, but is there any pressure-related analog process that may affect reaction and assemblages during decompression? So
absolutely. Oh, sorry. Yeah, go ahead.
No, I think, for example, if we cross the same two reaction boundaries, once with isothermal decompression and once with isobaric heating, should we expect similar overstepping in both cases?
Okay, I think when you think about the kinetic rate equation, from the free energy perspective, overstepping in pressure can give you the same effect as overstepping in temperature. The variation of free energy with respect to pressure is for a reaction is a volume change. The variation in a free energy change of a reaction with temperature is the entropy change. So if you decrease in pressure, you'll build up an energetic head, a driving force. So yes, from the perspective of the free energy driving force, yes, you will build up reaction infinity for sure. I think the temperature effect, I think, has a more important effect on this kind of basic Arrhenius relationship, where rate of reaction always goes up with increasing temperature, the rates of virtually all processes. increase. Now, nucleation might be a bit different because it's the temperature overstep that's really important. But in principle, yes, you could overstep in pressure just as well as you could overstep in temperature, and then you have to work out the balance between the free energy component of that process and the kind of activation energy controlled part.
Great, excellent. So we discussed already quite a lot in the discussion about overstepping, and now as a modeler, I'm interested to know, once the garnet, for example, nucleated, so once nucleation has occurred, what are the rate limiting processes for crystal growth, and are they the same in every rock?
Right, so this is the post-nucleation growth process. Okay, well, if you're knocking nucleation out of the collection of steps, then you're left with dissolution, transport, and then surface attachment. So the rate limiting step will vary on, I suppose the diffusion component would be, how effectively ions can move from the dissolved reactants through some sort of a tortuous grain boundary network to arrive, to be present or present probably in some sort of a fluid or loosely bound intergranular medium in the right proportions to attach onto the surface of the nucleated crystal. So to me, that would depend very much so on probably how much fluid there is contained in that intergranular medium. And I would think that the transport step would be markedly enhanced by, well, I wouldn't expect, this has been shown that the transport step is markedly enhanced by the presence of fluid. So fluid catalyzes reaction for sure. But supposing you have a fluid in the grain boundary, then what's a rate limiting step? Well, then you're left with the dissolution step or the attachment step. And the dissolution step, you're destroying a mineral with a nice crystalline architecture with lots of bonds. You are destroying that crystal. So, to me, that's a non-trivial energetic task, is to destroy that structure and then dissolve it. And maybe that becomes a rate limiting step. So I'm not really an expert on the details of the interplay between transport and dissolution and attachment. I think there are others probably in this audience who know a lot more about that than I do, but it's some sort of an interplay between these. And this is neglecting the difficulty of nucleation.
I'm happy you mentioned the fluid. So let's move on to higher temperature now. If I'm working with ultra high temperature rocks, how much should I worry about reaction overstepping in this case? And an associated question is there any influence of the presence of another fluid melt on overstepping?
Right, those are great questions. Now, Dave Ruby did a series of interesting studies with Adrian Brearley in the late 80s and early 90s. And I think he was concerned with how much overstepping there could be in melting reactions. And I think these were muscovite quartz to K feldspar sillimanite liquid melting reactions. And I'm fuzzy on the details. I haven't read these for some time, but they concluded that there was evidence of overstepping. This was partly based on seeded versus unseeded experiments. And their interpretation was that there were metastable reactions taking place over a range of temperature and timescales in those experiments, from which they concluded that if there were a nucleation problem, that this could also pertain to these melting reactions. Now, that's kind of a low temperature melting reaction, muscovite quartz. Ultra high temperature, I have no idea. Often you get kinetic assemblages, which suggest there's some sort of diffusion controlled process, which suggests to me that not everything is happening rapidly, or else you wouldn't get these coronal textures. But I'm just speculating.
Okay, just to follow up on that one, if you mentioned that we could have overstep on the melting reaction. In this case, could the overstep affect the melt composition?
Oh yes, and that's what Ruby and Burley found in their study. And I think it's just like anything else. I mean, if you predict I don't know, biotite sillimanite plagioclase quartz to react to make garnet cordierite liquid, and I don't know, maybe the garnet doesn't dissolve quickly enough, or maybe don't nucleate one of the products. Well, if you keep on heating the rock, something's going to happen, and presumably that's going to be one of these not equilibrium reactions. And so one predicts that there would be a consequence for that in terms of what the predicted melt phase would be. We don't have that in dehydration reactions because we're just kind of assuming it's a free hydrous fluid phase that's released and it disappears. But in terms of a melt phase, I would expect there would be a difference.
Okay, we are navigating through the PT path, Dave, and now coming back temperature. What about overstepping during retrograde reactions? Is it important to consider that?
Yeah, well, it's I'm not quite sure what the root of the question is. Like, we know that, or some people pose the question, why don't we turn all our prograde reactions backwards when we cool the rock off? Like, why do we ever pick up a kyanite schist off an outcrop? And I think that like quite a common explanation for that is this kinetic explanation. That is that just from an Arrhenius perspective, when you turn down the temperature, the rate of reaction goes down. The kinetics get poorer and poorer, and it's more difficult to get over that activation energy barrier as you cool. And so therefore you anticipate that there'll be a greater preservation potential in lower rocks. So I acknowledge that. I think that's important. But to me, at least as big a factor is the fact that when you have your kyanite schist, and you might say to yourself, well, as this cools off and comes back to the surface, why doesn't it turn back into a mud or a shale? But you've lost something on the way up. You've lost fluid. As you're dehydrating your way up from a mud to get to a kyanite schist, you've lost your H2O. And you can't turn a kyanite schist back into a mud unless you've put that H2O back into the rock. So, but it's gone. So unless it percolates in at some point, you're not going to turn it backwards. So I think there's a kinetic reason why retrograde reactions would be, you might expect overstepping, but I think there's this other factor as well.
And just a very personal question on that. In this case, if you say, okay, we overstep a reaction on the retrograde path, and then if we have a fluid, for example, entering the rock, and the rock will re-equilibrate partially, do you think this would affect the mineral composition that we model assuming equilibrium?
Yeah,
so
right.
Would the composition of the mineral be dictated by equilibrium?
Yeah, that's a good question. I mean, the way I see fluid infiltration during retrogression is that it has to somehow be injected along cracks or a grain boundary or something, and then you'll have the minerals, say the peak metamorphic minerals, say our kyanite schist, they're sitting there as kind of reactant reservoirs. And if you infiltrate fluid at, I don't know, much lower temperature, green schist facies conditions, then you'd start presumably the kyanite, staurolite, and so on from the higher grade mineral assemblage would be unstable, would start to dissolve, react with that fluid, presumably produce along the cracks or fractures the lower grade mineral assemblage for that reactive bulk composition, which somebody talked about yesterday. That would be you. Yeah, so I would view that as an extremely local reactive bulk composition, creating a mineral assemblage, and the rest of the minerals in the rock, they might have no connection whatsoever with that infiltrated fluid. And so essentially, they're not even part of the reacting system. So I'd anticipate you can have, you know, an unreacted part reflecting the dehydrated higher grade conditions, and then local development of this more hydrated assemblage reflecting this local reactive bulk composition for where the fluid infiltrated. And I think this is a really, really important point, in that I think you would have these two different domains. So you might grind up that rock that's partially rehydrated because it had some fluid infiltration. You grind it up, you'd end up with a bulk rock water content based on those hydrous minerals. You could make a phase diagram for that. But the phase diagram you would predict would probably not be representative of that selectively rehydrated mineral assemblage, because it would predict a single equilibrated mineral assemblage for that water content, rather than two different parts of the rock, most of which, say, would be unreacted, and the little bit which had was subjected to this rehydration, which would be the actual reactive bulk composition, which you might be able to simulate using approaches like you've presented.
Thank you. As you can imagine, I fully agree with this point. Thanks. We have really a lot of questions, Dave. So I'm going to ask more and more. The next one is, could the lack of correspondence between the pressure temperature at which the isoplates cross and the pressure temperature of the apparent peak temperature mineral assemblage field, as shown as Dave Waters yesterday, be a sign of kinetic effects?
Oh yeah, that's a good one. Let's go to, I'll go to Mark's example because I kind of like it, if I can find it. Yeah, so this is Mark Kinetic's work. This was an example of a blue schist from Sifnus, and they took the biggest garnets. Mark, correct me if I'm wrong. So, but I think they took the biggest garnets and looked at the compositions of the cores of the biggest garnets, plotted out the isopleths on this diagram, PT diagram here, and then for the interpreted reactive bulk composition, made this phase diagram. There's the garnet inline in dashed red. And then they contoured this. They made a reaction affinity map. And I'm not quite sure how this was done. Mark can clarify, but I think it might have been this subtraction method, the method one I mentioned. And so they found that the isopleths of the garnet were sitting up here, which is really quite different than the predicted garnet in curve. So I think they interpreted that the PT condition of that garnet bearing assemblage was reflected by those garnet isopleth intersections. But the implication was that getting up to that point, there might have been quite a long part of the history where the rocks might have wanted to form garnet according to equilibrium, but they didn't. So I am going to turn over to Mark because he did the work, so he better clarify this.
Thanks, Dave. 2 points. Firstly, you described what we did very neatly, but I would like to add that almost all of that work, except for the calculation of the energy of overstepping, wasn't actually me. Most of it was Besim Dragovich's work.
Okay.
But yeah, that's essentially what we did here, and what it looks like is that there might have been substantial overstepping before garnet first grew. There are some uncertainties associated with that. One of the big ones, as we heard a little bit yesterday, and I think we'll hear from Jacob tomorrow, the position of that quote-unquote garnet inline is incredibly sensitive to the thermodynamic data set that you're using, and specifically things like the amount of manganese in it. And then there's also been work done recently, particularly by Frank Spear and colleagues, that suggests that the use of isopleths for kind of the intersection of where did garnet first grow comes with uncertainties in cases where overstepping has occurred. And so I encourage you to read Besim Dragovich's paper on this, and our review in Carlson et al. And some of Frank Spear's recent work.
Yeah, I think that's a terrific point to make. Thanks, Mark. I think the work that Frank Spear and Adrian Castro and Oliver Wolf have been doing, this is well worth looking at as well. I think one of the implications of this work is that the garnet zoning that develops from an overstep scenario, like suppose in this, like the example Mark has shown here, garnet doesn't grow and then finally it nucleates and grows with overstepping. You can predict that that will develop a zoning pattern, which actually looks very similar to the zoning pattern as if you were to interpret a prograde fractional equilibrium growth of shells of garnet progressively along this PT path, along this dashed line here. And so to me, it raises a really important question as to how much we can trust the zoning, like say classic bell-shaped zoning, as an indicator of prograde fractional crystallization, or whether it could indicate growth after an overstepping period. The final point I'll make is that Freya George and her study with Fred Gades, they thought about this a lot. And so I'm getting a little bit past my familiarity here as to the arguments one way or the other. But I think it is it's kind of a point that's worth thinking about.
So thank you, Dave. Thank you, Mark. We can take one more question. So the question is, can inhomogeneous distribution of stresses at the thin section scale provide the necessary energy to recrystallize parts of the sample, but not other parts?
Oh, different stresses at the grain level. So this is beyond just Ostwald ripening. Ostwald ripening is the idea that small grains with their relatively high surfaces to volume ratio tend to eliminate the higher free energy surfaces by amalgamating into larger crystals. That's Ostwald ripening. That's thought to be quite a small energetic driving force in metamorphic recrystallization. But the other question about variations in pressure causing, say, from deviatoric stress, maybe whether that might facilitate solution dissolution. I don't have too much to say about that. I know that if you look at an average thin section of a sandstone, if any of you have looked at the sandstone, look at the grain-to-grain contacts of a sandstone, it's very clear that where grains are impinging on each other, they dissolve and make concavo-convex contacts and sutured contacts, and you get cement redistributing from just stress that way. So that would appear to be stress-induced recrystallization. In the metamorphic regime, I'd have to think about it. I'm sure it happens. I'm just not sure how big a factor that would be. It's a good question.